Okay, now we want to write our Verilog code to describe the circuit based on this state diagram. So we need to open the quarters 2 so that we can write the code. So let's have our quarters 2, and we actually need this. Okay, so we still want this, the state diagram, right? And actually what we need to have is, before that, we need to have this, right? Okay. So we want to describe this circuit actually, right? And the behavior is based on the state diagram. So we have this signal, and in Verilog, we need to change a little bit this one. This one we don't want y. We change to y1, and this one is y0. This one small y1, and this one is small y0, right? Now in Verilog, we need to start a new project. So just go to new project wizard. As usual, we create the directory or folder for the project. So maybe in the finite state machine folder, give it a name as an example1, and let's name this as this also. Click snack, and we don't want to add any file to the design, and this one lets the computer select the device automatically, as we only want to simulate the function of this, not to do the hardware implementation. So just click finish here, and now we need to create a new Verilog file here. Click OK, then we have this. So we have our module name. Module, the name is this, right? And what we have here at the input and output. So we'll have clock. We actually have a reset signal. So we have clock. So the name is CLOCK. We have reset. We have input W, and also we have Z. All right, the output is Z. So the input will be clock, reset, and W. All are 1 bit. The output will be Z. And we have internal wire here, signal here, capital Y1 and capital Y0. small y1 and small y0, and because um, we will describe this using behavioral modeling, and of course it will be inside the always block, so this must be declared as right. Yeah, and also this is the output from these flip-flops, and the flip-flop is also described using behavioral modeling. So inside always block, so this should be right as well, and the size is 2-bit, right? So we can have right y 2-bit 1 to 0, y big capital Y and small y, right? And as we want to describe the um, finite state machine, so it is better to have the state name, yeah, instead of using 0 0 0 1 1 0. So we use state name just like this, a b c. All right, so we can do that by representing 0 0 with a, 0 1 with b, and 1 0 with c. So we can use that using parameter declaration parameter, and the size also 2-bit. A is equal to 2-bit 0 0, right? And we have b is 2-bit 0 1, and lastly we have c 2-bit also 1 0. That's it. Okay, should be done now, and now we can create this part of our circuit. This is the easiest part that we can describe in Verilog, because it's just two flip-flop or a register. All right, so we call it as state register. Okay, and here we can use always. All right, and the clock is post edge, positive edge triggered, post edge clock, and we have reset signal actually, and the reset, let's make it active high, right? So asynchronous reset here, active high, so post edge reset. Okay, so for our flip-flop or register here, when reset is active, in this case equal to 1, the output of the register or y, yeah, small y, should be equal to 0, or in this case is at state A, we should be in state A, right? 0 0 here means state A, so we can replace 0 0 with A, because we define already here that A is actually equal to 0 0, right? And again, we need to remember that when we want to describe the synchronous uh, sequential circuit, so the assignment that we use is the non-blocking assignment here, right? If the clock is not active, in this case else, yeah, else means that if reset equal to 0, y should be, all right, the output here should be equal to y, capital Y here, all right, capital Y here. So done for this. So we will have these two flip-flops with this part of code, right? Now we want to define this and this. So you can define You can have two separate code always block, or you can combine in one always block. So in this case, I just combine this in one always block. Yeah, so we can have something like this. We call it this one is the next state logic, next state logic, next state, and this one will be the output logic. All right, and we describe this using the behavioral modeling. All right, so we use always block. So this combinational circuit is depend on what output input. So in this case, so this one will depend on W and also small y1 and small y0, right? Or W and small y. And this Z will depend on y, small y here. All right. So we can use always block. The sensitivity list will be W or Y because this circuit will depend on W and Y, and this one also will depend on Y, right? And we can use case statement, all right? So if Y here, all right, if Y here 0 0, for example, 0 0 means that A, okay, when Y or the state of the finite state machine is A, what we need to do if W equal to 0? What we need to do if W equal to 1, all right? So for example, if we are at A, so Z should be equal to 0. And if also if we are at A, when W equal to 0, so the next state, which is this signal, should be A also. All right. But if W equal to 1, the next state here should be W equal to should be Y equal to capital Y equal to B or 0 1, right? So we can use case Y, right, based on the state of the finite state machine, right? Case Y. So if Y is at A, right, or 0 0, A here means 0 0. So if Y equal at A, so we will have many statements. Of course, the first one is when we are at A, Z should be equal to 0, right? And we look at W. So W, we can have two conditions. So where the first one is if W equal to 1, all right? So if W equal to 1, so the next state, which is this one, all right, should be equal to 0 0, A, should be equal to A. So if W equal to 1, so Y should be equal to A, right? If W equal to 1, sorry, should be equal to B. If W equal to 1 means that we go to B. All right, if W equal to 1, we go to B. So means that the next state must be B or 0 1 in our case. Yeah, B is 0 1. So should be B, and B is 0 1 here. All right. Else, we can write here else. If W equal to 0, we should remain at A. Means that this signal must be A. All right, 0 0. If W equal to 0, means that the next state must be A. Okay, that's it. And we can have N here. All right. And when we at B, or the current state is B or 0, 0, 1, right? 0, 1 means that B, so Z should be equal to 0. So Z should be equal to 0. But, and if we are at B also, when W equal to 1, so we should go to state C. All right, if W equal to 1, so the next state here must be C or 1, 0. All right, 1, 0. Else you go back to A. All right, and done for B. For the C, you can have begin, and C, our Z should be equal to 1 now. And if W equal to 1, based on this, when we are at C, when W equal to 1, so we stay at C, and W equal to 0, we go back to A. All right, so just like this, Y equal to C, and go back to A. And remember, when we use case statement, we need to have all the combination, all the possibilities for Y. So in this case, we only have three possibilities for Y. We need another one, which is 1, 1, just like here we have 1, 1, and this 1, 1 is don't care. So we can use default. So default, and for this default, we don't care whether W is 0 or 1, and Z should be always equal to, in this case, is don't care. Z is don't care, so we can have something like this. Z equal to, how to write don't care in Verilog. So this don't care is 1 bit, so it should be binary X, yeah. And Y is don't care also, so it should be 2 bit now for Y, right? Then we should have our N here, and case, this case, and we should have N module here. All right, so now this is our Verilog code to model this circuit. All right, and the behavior is based on this. Okay, so now we can see that we have skipped this process, yeah, this step. All right, so no need to have or to derive the state assigned table, no need to derive the k-map, and no need to derive the Boolean equation. We can straight away write the behavior of our finite state machine and let the Verilog compiler to generate the circuit for us, right? In this way, if we have more than 3 state, we have 10 state, we have 20 state, or more than that, should be no problem because we use computer to generate the circuit. All right, we just describe the behavior of the circuit instead of derive everything. Yeah. Okay, so that is why we use Verilog to design the complex circuit. Yeah. So now let's simulate the design. So we need to save this. This example 1, okay, and we should synthesize this. Let's see if any problem, error. Yes, we have 2 error, and this is syntax error, should be easily fixed because we missed some expected expecting end here, so we can double click here. Yes, we have begin here, but we don't have the end statement, and this is not allowed. And this is yeah, just the same error because of this error. So just again we have yes here. So because we have this because z is on the left hand side of the assignment, and the variable must have a variable data type, just like I said before this, because the z here is the variable inside the inside the always statement. So we forgot this that the z must be declared as rect as well. All right, so we have rect here, and now should be okay. All right, so we have only one warning, and this warning is of course from the disable of the parallel compilation because of the license, and this should be no problem. All right, for the design, and we have this already, so we can now design our testbench for the simulation. So let's do the simulation by creating the new Verilog code, okay, for the testbench. So let's set the time scale to 1 nanosecond to 1 nanosecond. And the module name, maybe we use FSM example one. The name is this testbench for this, and we can have um, the input and output for the testbench, so we can use the same one, right? So clock, reset, and w is the input for the testbench, and remember we should declare this as right in testbench, and the output should be declared as wire in testbench. This is that. And now we instantiate our design. So our design is FSM example 1. Yeah, this name, right? And the name for the instantiation module is TB or any other name that you like. And we do the port map because we use the same name here, so we can actually use this. Just copy this and put here, so we can get the connection already. And we have initial block here to set the signal that we want to look at. So we can use monitor. We want to plot the time, and we want to look at this. All right, and it should be in the form of binary. Okay, until here, and this is mapped to this port also, so we can just copy and paste. Done. We can have and here, and we need to create the clock as well. the clock and reset signal for the time 0 at initial. Maybe we can have reset signal to set at 0 first, and the clock is start from 0. Okay, and we can have always this one is uh, to create a square wave, yeah, of clock signal. So every 10 nanoseconds, so we toggle the clock. You can do like this, or you can use forever clock, yeah, same thing. All right, now we want to give the stimulus to our finite state machine whenever what happen whenever w equal to 1 for one measurement, or if we have two measurement or three measurement, we have w equal to 1 for two consecutive measurement. So what happened to the output? All right, so we expect that if w is only equal to 1 for one measurement, the next measurement w equal to 0, so we expect that that should be remain 0. And if we measure the w equal to 1 for two consecutive measurement or more, so z should be equal to 1. All right, so what we need to do is maybe we can have something like this. All right, so we have the clock signal. Just like this. So for this is clock, and for the w, all right, to consider that w equal to 1 is that it should be 1 for one consecutive clock. For example, if our w is here, all right, and because this is positive edge triggered, so it should be triggered here. And when we see that, when we have the signal like this, all right, means that our system read this as 0, yeah, because it is not the w is very short that our system cannot detect, because for the next clock edge, positive clock edge here, the signal is 0 already. So this is 0, all right, the first clock edge 0, and the next clock edge is 0 already. So this is considered a false signal, all right, not count as a w equal to 1. So to count whether w equal to 1 or not, so you need to have this, w should be at the edge of the clock. So in this one, although you have very short w, but because it going to 1 at the clock edge, so this should be count as w equal to 1 for one measurement. All right, and if it is go down already here, means that w go to 1 only for a short of time, so z should be equal to 0. But if, for example, if W is something like this, all right, means that it's 1 here, and the next measurement is W equal to 1 already. So two consecutive clock measurement, uh, the speed is over the limit, so Z now should be equal to 1 here. All right, so this should be uh, our signal that we should generate in our test bench. So let's create the signal so that we can see this in simulation. So let's have our W. Maybe before that we should reset our finite state machine first. So the reset signal here is at 0, so we reset first until this is 10 nanosecond. All right, because our clock is the period is 20 nanosecond, right? Because we changed the clock state from 0 to 1, 1 to 0 to 1, 1 to 0 every 10 nanosecond here. So this should be 10 nanosecond, and this is, should be 20 nanosecond. This is 30 nanosecond, and so on. All right. So at 20 nanosecond, we make the clock to inactive, or put it make it 0, make it low forever. All right, and our W here should be right. So let's see if this is our W. So maybe we have 0 first, and here we make it 1. So at this is 40, this is 50, right? 50. So maybe at 48 or 45, all right, we go to 1, and just before the next measurement we go down. All right, so let's say this one is for about 20 nanosecond, go down and down until this one is 40 nanosecond, this one 40 until here, and maybe we have this one is how many measurement, right? So one measurement, two measurement here, and we going down already. So this is high for 40 nanosecond, means that there are two consecutive measurement that the speed is exceeding the speed limit, and 0. And let's see what happened to this. Yeah, so we will create the simulation like this, and we expect that here Z should be equal to 1, right? So how to do that? So let's do this. So at we should have, initial, begin, So at 0 we should have reset. We make the reset. So here maybe we don't need. So at here maybe we don't need this reset. So just clock equal to 0, and our reset here should be equal to 1, so that at time 0 we start to reset and make w equal to 0 first. All right. And at time 20 nanosecond, all right, the next 20 nanosecond, so we make our reset to be 0. All right, and w still equal to 0 here, so no need to change. And at here, another 20 nanosecond. So we want to be at 48 nanosecond, for example. So this should be because this is 20 to 48 is 28 nanosecond. 28 nanosecond. So we can have 28 nanosecond later. We say that W should be equal to 1. All right. And it will be 1 for 20 nanosecond. So about 20 nanosecond later, W is go back to 0. And for 40 nanosecond, W is equal to 0, and it will go to 1 again. So W equal to 1 there. And this one is for about 40 nanosecond, which means or represent 2 consecutive measurement. So about 40 nanosecond. So we have W equal to 0 now. Go back to 0. And maybe we have the next one. Yeah, for 3 consecutive measurement. So we can have something like another 20 nanosecond. We go back to high again, and this time it's high for 60 nanosecond. So let's see what happened. And we stop the simulation after 40 nanosecond. So we just stop the simulation here there. Okay, and module. All right, so this will be our test bench, and we want to save our test bench, and the name should be like this. Okay, so save our test bench, and we can check for any syntax error by click synthesize, and here again clock. We're not using CLK, we're using CLOCK clock. This is also the same. CLOCK clock. All right. Okay, check again, and there is no error. So same warning, should be okay now. And now we want to simulate our program. So just go to setting. You need to do some setting, remember need to select the tools, which is the model sim Altera, and we need to use the test bench and click the new, and the name should be the same as our file name, and here we need to add the file, so must be this one. We add here, click OK, OK, and OK. So done. So now we can click this RTL simulation or functional simulation. Just click this and wait for model sim Altera to be invoked. All right, there. Okay, and try to zoom all. And here we can see that very clearly that whenever W equal to 1 for one measurement here, this is one measurement. Okay, when W equal to 1 and Z is equal to 0, and for the next measurement and this measurement, all right, this is the first measurement, second measurement, and Z and W still equal to 1, and we can see that Z is now equal to 1 already here. All right, and when W go down to 0, and Z should go down to 0 as well, and later we have W go to 1 already, go up to 1 already. Here go to 1 again, and for the first measurement here Z still equal to 0, but for the second measurement here Z is going to 1, go to 1 already here, and the third measurement is still at 1 here. W equal to 1 here means that Z should be remain 1 until the next measurement here. The W going down to 0 already, and Z is go to 0, means that no need to slow down the vehicle already because W already go down to 0. All right, so this simulation is correct based on our specification in this uh, for this finite state machine. All right, so that is for today. So we will look at the melee type state machine next week here, where we will look at the same example, right, which we want to maintain the speed of the vehicle, all right, by measuring the speed at a fixed interval time, all right, and when the speed is exceeding the limit for the two consecutive measurement, the speed is reduced. But if the speed is exceeding only one measurement, so the speed is not reduced. It will measure for the second time. All right, so the same example here, we will look design the finite state machine, but using the melee state model or melee state machine. Okay, thank you for today.